In this video here, we're going to take a look at graph theory. Now, as we progress through the remaining videos in this chapter here on graphs and networks, and also just decision maths in general, it is important that we do familiarize ourselves with some basic terminology and definitions. So, in the graph G below, so that's this graph here, right? The vertices, which are just sometimes called nodes, are A, B, C, D, and E, right? They're the points on our graph. Now, the list of vertices is sometimes called the vertex set. And the edges, which again are just sometimes called arcs here, are given as, I've got AB, we've also got AD, I've got BD, I've got BE, I've got BC, I've got CE, and also DE. And the list of edges is sometimes called the edge set. Now, the next thing that we need to learn about here is what's called subgraphs. Now, a subgraph of G, that's this graph here, is a graph where the vertices belong to G and the edges also belong to G. So, simply put, it's a section of the original graph. So, some possible subgraphs could include the following. So, I've got this example here, right? Notice we've just got this section of the graph. So, A, B, D, as we can see here. And another example could include this graph here, right? This is a subgraph of G. So again, I've got a portion or a section of the original graph, as we can see here, B, C, E. Okay. So for the next section here, we have the degree of a vertex. Now, the degree or valency or order, you can use those terms interchangeably, by the way, they all just mean the same thing. Of a vertex is the number of edges incident to it. Now, we say that a vertex and an edge are incident if the vertex is at either end of the edge. So what I've got here then is our graph G and also this table here. So this table here then shows each vertex from the graph G, and also, I mean, it's not complete at the moment, but we'll complete that in a moment, the degree for each respective vertex, right? So A, B, C, D, and E. So let's just quickly fill out this table here, right? So let's just start with the vertex A here. So, how many edges are incident to the vertex A? Well, I've got this edge here, AB, and also this edge here, AD. So, the vertex A has degree 2. The vertex B then, how many edges are incident to B? So, I've got 1, 2, 3, 4. So, the vertex B has degree 4. For C then, well, that's essentially just this vertex here, right? But on the other side now. So again, that has degree 2. For the vertex D then, how many edges are incident to D? I've got 1, 2, and 3. So the vertex D has degree 3. And again, the same is true here for the vertex E. So 1, 2, and 3. Like so. Now, if the degree of a vertex is even, we say it has even degree. So based on this table here then, A, B, and C have even degree. So A has degree 2, B has degree 4, and C has degree 2. So A, B, and C then have even degree. And in a similar fashion here, D and E have odd degree, right? They're both of degree 3. So let's just quickly run through some definitions here for traversing a graph. So a walk is a route through a graph along edges from one vertex to the next. A path is a walk in which no vertex is visited more than once. A trail is a walk in which no edge is visited more than once. So pretty similar to a path, but the difference here is we're talking about no edges being visited more than once as opposed to vertices. Now, a cycle is a walk in which the end vertex is the same as the start vertex, and no other vertex is visited more than once. And then finally, a Hamiltonian cycle is a cycle that includes every vertex. An example of a walk would be A, B, C, E, D, A. So A, B, C, E, D, A. So basically going on the outskirts here of our graph would be an example of a walk. Now for a path then, an example here would be A, B, C, E, and D. So pretty similar to walk here. Again, you can find multiple examples here, right? So that would be an example there of a path. Now for a trail then, an example here would be D, E, C, B, A. Again, there's multiple different trails that you could include there. Now, an example of a cycle here would be D, A, F, D. Okay, again, there's multiple different cycles you could do here. For example, I could do A, B, F, A. That would be another example of a cycle. And then finally, a Hamiltonian cycle here would be, so let's just go through this in full here. So D, E, C, B, F, A, D. That there would be an example of a Hamiltonian cycle, right? It's a cycle that includes every vertex. So for the next section here, we have connected graphs. Now, two vertices are connected if there is a path between them. And we say that a graph is connected if all its vertices are connected. Now, the graph below here would be an example of a connected graph. And just notice then that a path can be found between any two vertices. And just notice here then that the graph below, so that's this graph here, is not connected. So as an example then, there is no path from D to E for this graph here. So in that case then, this graph here is not a connected graph. And now for the very last section here then, we have directed graphs. So if the edges of a graph have a direction associated with them, they are known as directed edges. And the graph is known as a directed graph, which we often just abbreviate to digraph. And the graph below here would be an example of a directed graph. And just notice here then that each arc has a direction associated with it, right? As you can see here, indicated by the arrows. Now, in any undirected graph, the sum of the degrees of the vertices is equal to the number of edges multiplied by 2. And as a result, the number of odd vertices must be even. Now, this could also include 0. And this result here is known as Euler's handshaking lemma. So that is everything that we need to be aware of here then for graph theory. So to finish with then, let's just work through two examples together. So let's just get started here then with question 1. Now, as we can see for question 1 here, it's split into two different parts. We've got part A and part B. So let's just begin then with part A. Now, all we want to do here then is just list the order of each vertex for the graph below. And as we can see here, it is a pretty simple graph, but it doesn't really matter too much, right? If anything, it should make this question a little bit easier, okay? What I've also got here on the right is a table. So in the left-hand column, we've got the vertices or each vertex from this graph. And then in the right-hand column here, that's what we're going to fill out. This here is the order of each vertex, okay? So don't forget here, when we talk about the order of a vertex here, what we're talking about then is how many edges are incident to that vertex. Or in other words, how many edges actually connect to that vertex, okay? So for example then, for the vertex A here, I've got 1, 2, 3 edges incident to A here. So it has order 3, okay? Now for the next vertex here, B, well, how many edges are incident to this? So I've got 1, 2, 3. So again, the order is 3. Hopefully, nice and straightforward. Moving on to the next vertex here, C, how many edges are incident here? So 1, 2, 3. So again, this has order 3. Hopefully not all order 3. Let's keep going. So what do we have next here? So let's go to D then. So again, how many edges are incident to D here? So 1, 2, 3. So that has order 3. Moving on then, vertex E here. So vertex E has order 2 because there's 2 edges here incident to vertex E. So E then has order 2. And then finally, for my final vertex here, F, how many edges are incident to F here? So 1, 2, 3, 4. So vertex F then has order 4. Okay. Now, I did jokingly say, hopefully they don't all have order 3. That would actually be impossible, right? I can't have all my vertices being odd. So you wouldn't actually expect that, but just so you're aware there. There we go. So that is my solution to part A. Let me just make a note here. Perfect. So that gives us the solution there to part A. Now, for the final part of this question, part B, let's just do this underneath here. So it says then, verify that Euler's handshaking lemma holds for the graph above. So for Euler's handshaking lemma then, this just states then that the sum of the order of the vertices here is equal to 2 times the number of edges, or the number of arcs, right? Whichever you prefer to call that. So let's just start then by finding the sum of the order here. So 3, 6, 9, 12, 14, and then 18, right? So sum of the order of the vertices. So as we just deduce then, that is 3 plus 3 plus 3. Let's write this down in full anyway. So 3 plus 3 plus 3 plus 3 plus 2 plus 4. As we just evaluated then, that gives us 18. Perfect. So how many edges then do we have for this graph here? So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 9 edges. So 9 edges on the graph. So therefore, 18 here. So sum of the order of the vertices. So I'll write this down in full again. So 3 plus 3 plus 3 plus 3 plus 2 plus 4 is equal to 2 lots then of the number of edges, which is 9 in this case, right? So 2 times 9. I get 18 here on the left-hand side. Obviously, we get 18 again on the right-hand side. So 18 on the left-hand side, 18 on the right-hand side, and therefore then Euler's handshaking lemma holds. So Euler's handshaking lemma holds. Okay. And there we have it then. So hopefully nice and straightforward there. That gives us the solution to question 1. And then finally, to finish with here, we have the very last question, question 2. Now, as we can see then, question 2 here is pretty short. So what I've got here then is a graph that has 6 nodes and 10 edges. The order of the vertices is given as follows. So I've got x plus 1, 2x, x minus 1, x plus 2, 3x, and then finally 2x minus 2. And all we want to do here then is just find the value of x. So to answer this question here, what we need to do then is make use of Euler's handshaking lemma, right? So what I need to do here is add the order of the vertices together. So sum the orders here. So let's just do that to begin with then. So what have I got here? So therefore, x plus 1. So x plus 1 plus 2x. So plus 2x plus x minus 1. So plus x minus 1 plus x plus 2. So plus x plus 2 plus 3x. And then finally plus 2x minus 2. Now, by Euler's handshaking lemma here, the sum of the order of the vertices will be equal to 2 lots of the number of edges, right? So 2 times 10 here. So 2 times 10, okay? So let's just simplify the left-hand side here. So what have we got here then? So x plus 2x, that's 3x, plus x is 4x, plus x is 5x plus 3x, 8x plus 2x is 10x. So we've got 10x there. I've got plus 1, minus 1. They just cancel. So they just cancel. I've got a plus 2 here and a minus 2 there. So again, they just cancel. Okay, so on the left-hand side here, nice and straightforward. Then it just simplifies to give us 10x. So we get 10x on the left-hand side. And then on the right-hand side here, 2 times 10 should be very straightforward. It's just simply 20, right? So 10x is equal to 20. So nice and straightforward then. X here is simply equal to 2 there. Okay? And there we have it then. So hopefully quite a nice straightforward question to finish with there. And there we have it then. So that gives the solution here to the very last question, question 2. And that brings us to the end then of this video here on graph theory.